And so what happens if the block is moving vertically instead? If it's not on a horizontal surface, if it's hanging from a spring, how does that affect the energy? Well, it turns out that it does not affect the way we think of it. We can still consider maybe a mass on a spring that's been pulled down to a certain point, which again sets the amplitude of the motion, which sets the energy of the system. And then as the spring pulls the block up, as it passes through its equilibrium position, it would again have only kinetic energy. And so we would be able to set these two expressions equal to each other to determine a maximum speed, or if we knew the maximum speed, to determine an amplitude or a value of k. So it's the same sort of thinking involved. It would reach a highest point that would be symmetrically placed above the equilibrium point compared to where we originally pulled it down. And again, it would have all elastic potential energy at that point. And then at any point along the way between this maximum height and this lowest height, the system would have two kinds of energy, both kinetic and elastic potential energy. But maybe you're thinking, well, when it's vertical, shouldn't we include gravitational potential energy? Shouldn't we include mgy? It turns out that in nearly all situations, we are able to ignore this. And I'm just going to prove that to you looking through some algebra here. You won't be asked to redo this sort of algebra again. It's just mainly to prove that it's fine to make this assumption. So the key difference here is that the spring is relaxed, not really at the equilibrium point, but at the point before the mass is even attached to it. So we would have our 0 point for gravitational potential energy at that lowest point wherever we pull the mass down to, but the 0 point for the elastic potential energy would need to be where the spring had nothing pulling on it at all, which means that there's this extra distance we would have to take into account, mainly the distance between the 0 point of elastic energy and the equilibrium point of the system. And so I've called that x sub o on this diagram here. So how does that change the way we're thinking about these various values of energy? Well, for the first one, our energy would still be only elastic potential energy, but the amount stretched would have to be measured from that purple dotted line, from that 0 of elastic potential energy, meaning that it's the amplitude, the distance we pulled it, and also the distance that the weight of the object pulled it. All right, so right away the math is going to look a lot messier. And if we looked at the equilibrium point, where before we were able to just say it was all kinetic energy, well, now this point is above the lowest point, so it has gravitational potential energy, but it also still is below the 0 point of elastic. And so at this location, we would have to include both of those types of energy. And it looks pretty ugly. But again, I'm going to show you with some algebra that it actually comes out to be the exact same thing we had before, and we're able to ignore the fact that this system is vertical instead of horizontal. One of the things we'll need to consider, though, is how at the very beginning, when the mass was first put on the spring, that would have set the equilibrium position. And so recall that with equilibrium, the forces are balanced. So this equation here comes from not looking at while the mass is moving, but just determining where that equilibrium point is. So the spring would have stretched this distance x sub o, and so the spring is exerting a force k x sub o. and then the weight of the object pulling down is mg. So those two things would have to balance at the equilibrium point, and that gives us an expression that the value of k would be mg divided by x sub o. I'm going to use that on the next slide here. So just starting with these two expressions, again, this is just coming from setting the potential energy at the lowest point where it's all elastic potential and saying, oh, well, all of that energy would have to be present in the form of kinetic, elastic potential, and gravitational potential at the secondary point. Okay, so you're just saying that the total energy stays the same. We're just going to do some algebra here. So to use the binomial theorem and multiply out the a plus x sub o squared, and this is what you get when you distribute that 1/2 k to each of the terms. This is how the left-hand side turns out. And then we can notice that the 1/2 k x sub o squared actually ends up on both sides of the equation, so that can be canceled out. And again, it still looks pretty messy, but again, recall that k was equal to mg divided by x sub o. We got that from the equilibrium condition. And so we can substitute this k here for, or with that expression, mg over x sub o. Again, do a little algebra. That term just becomes m times g times a, but hey, that's what we have on the other side of the equation too. So we end up with a very simple result by just, again, putting this all together, that if the spring is on, if the mass is on a vertical spring instead of a horizontal spring, we get the exact same thing we would get as if we had completely ignored gravity. Gravity is not what is causing the mass to go up and down. Gravity is not what's driving the simple harmonic motion. It is the spring force that's doing that. You can't make something oscillate without the spring. It's not gravity that's doing it. It is the spring that is doing it. And so it should make sense that we should be able to ignore the effects of gravity. And so that's just very handy. This is also true. It can be shown like if the object were on an incline and oscillating up and down an inclined surface at an angle, same sort of thing happens. The gravitational ideas, the angle and so forth, do not affect the rate at which something oscillates.